Vibration Analysis Diagnosing Misalignments, Step-by-Step Guide to Detect and Fix Misalignments. Diagnosing Misalignment Overview. This opening slide introduces the overall theme of the presentation, Diagnosing Misalignment. Misalignment is one of the most common and significant mechanical faults encountered in rotating machinery. Establishing the context early helps the audience understand the importance of accurate diagnosis, proper corrective actions, and the consequences of ignoring misalignment, which include excessive vibration, premature bearing failure, shaft cracking, and reduced operational reliability. In industrial environments, misalignment is responsible for a large percentage of chronic maintenance issues, and early detection is essential. This presentation will systematically cover all relevant misalignment types. Real case examples, diagnostic techniques, waveform indicators, frequency domain symptoms, and applicable standards. It also introduces related issues such as soft foot, bent shaft, and cocked bearings, which often mimic misalignment symptoms and require careful differentiation. The slide sets expectations for a technical, engineering-oriented session with diagrams, fault signatures, and a flow-based diagnostic framework. The agenda slide outlines the structure of the entire session, guiding the audience through each major topic from introductory concepts to advanced diagnostic methods. The agenda includes Introduction to Misalignment, Causes and Failure Mechanisms, the three primary types of misalignment, offset, angular, and common, severe misalignment characteristics, distinguishing misalignment from unbalance, addressing false 2x peaks, effects of temperature on shaft alignment, time waveform interpretation, real-world case studies, and secondary fault conditions such as soft foot, bent shaft, and cocked bearings. The audience will also be presented with multiple diagram placeholders for vibration signatures, misalignment flowcharts, and thermal growth illustrations. This structured overview ensures participants understand the progression from theory to practical analysis and final recommendations. Introduction to Misalignment, Causes of Misalignment. Misalignment refers to the improper relative position of coupled machine shafts, and it is one of the leading causes of increased vibration amplitudes and accelerated wear in rotating equipment. Misalignment can occur in machines ranging from pumps and motors to turbines and fans, and typically manifests through characteristic vibration signatures, noise, heat, and mechanical degradation. The introduction provides a conceptual overview of why misalignment occurs and how it interacts with machine components. Improper installation, thermal expansion, excessive load conditions, and foundation distortions all contribute to misalignment. Understanding misalignment requires examining the relationship between shaft motion, bearing load distribution, and transmitted forces during rotation. Identifying misalignment early prevents energy loss, shaft bending fatigue, seal wear, and repeated coupling failures. This section introduces the three fundamental misalignment categories and sets the stage for deeper analysis in upcoming slides. Misalignment may arise from multiple root causes, including installation errors, thermal growth, uneven machine bases, soft foot conditions, incorrect coupling assembly, pipe strain, and operational shifts. Even minor structural changes can alter the shaft centerline, leading to misalignment that worsens over time as loads vary. Thermal changes are particularly significant. Machines often heat unevenly, causing shafts to expand in different directions, changing the alignment condition under load. This slide explains how both static and dynamic factors contribute to misalignment, emphasizing why laser alignment performed in cold conditions may not reflect actual running alignment. Understanding these causes helps maintenance professionals predict issues and implement preventive alignment strategies aligned with best practices. Key points: Misalignment, Types of Misalignment, Overview. This slide summarizes the primary indicators of misalignment, including elevated vibration amplitudes at 1 order and especially 2 orders running speed, excessive axial vibration, phase inconsistencies across measurement locations, coupling deformation, excessive temperature at bearings and couplings, and noise. Misalignment affects each machine differently, depending on stiffness, coupling type, load distribution, and operating speed. A properly aligned machine distributes forces evenly along the shaft, whereas misalignment creates cyclical forces that distort shaft motion. Key points also include recognition of misleading symptoms, such as how unbalance can create harmonic energy that resembles misalignment, and the necessity of multidirectional vibration measurements. These fundamentals are essential for developing diagnostic accuracy across varying machine types. This slide provides an overview of the main misalignment categories: offset, parallel, angular, and a combined misalignment known as common misalignment. Offset misalignment describes shafts whose centerlines are parallel but not collinear. Angular misalignment occurs when shafts meet at an angle but intersect at a common point. Combined misalignment integrates both conditions simultaneously and is the most frequently observed in industrial machinery. Each type generates different vibration characteristics, unique frequency signatures, and specific mechanical wear patterns. Understanding the geometry behind each type is critical for proper diagnosis and corrective alignment procedures. This slide prepares the audience for detailed analysis contained in the subsequent slides. Diagnosing offset, parallel, misalignment, diagnosing angular misalignment, diagnosing common misalignment. Offset misalignment produces strong radial forces that act on the bearings, leading to elevated radial vibration levels. Typically, this fault produces high amplitudes at 1 order and 2 orders running speed, along with possible harmonics depending on the severity. Offset misalignment distorts shaft motion, often causing elliptical orbits. Technicians frequently observe greater vibration in the horizontal direction for horizontally mounted machines due to directional stiffness differences. This slide explains diagnostic indicators, including waveform distortion, directional patterns, amplitude differences across bearing locations, and how vector-phase relationships help distinguish offset misalignment from unbalance. A diagram placeholder is provided for visualizing shaft centerline displacement. Angular misalignment produces more axial than radial vibration and especially affects the coupling faces. One of the most notable signatures is elevated axial vibration at 1 order and 2 orders running speed, which is not typically seen in unbalance. Angular misalignment also creates torsional stresses across coupling components, leading to abnormal wear patterns. The slide explores vibration indicators, phase deviations, and coupling condition clues. This misalignment type often creates heat at the coupling or bearing housings due to uneven loading. Distinguishing angular misalignment requires cross-channel measurements and verifying phase angles for directional consistency. Common misalignment represents the simultaneous presence of offset and angular misalignment, and is the most frequently encountered in coupled machine systems. Its vibration pattern typically includes high amplitudes at both 1x and 2x components, increased axial and radial vibration, and inconsistent phase patterns. Because common misalignment creates complex force interactions, it often leads to premature bearing wear, repeated coupling insert failures, and shaft fatigue. The slide describes how to detect this fault through waveform distortion, multi-axis readings, and comparative data between machine ends. A placeholder diagram is included for illustrating combined shaft displacement characteristics. Severe misalignment, or unbalance, beware of false 2 orders peaks. Severe misalignment results in significantly elevated vibration, often accompanied by strong harmonics, erratic waveforms, and excessive heating at bearings and couplings. Such conditions may cause the coupling to seize, rubber inserts to tear, or shafts to bow due to cyclic bending stresses. This slide emphasizes the urgency of detecting and correcting severe misalignment to prevent catastrophic failure. It also discusses how severe misalignment amplifies axial forces and contributes to looseness, cracked bases, and resonance-coupled problems. This slide helps the audience differentiate misalignment from unbalance, 2 faults that frequently get confused. While unbalance primarily produces a dominant 1-order vibration in the radial direction, misalignment generates significant axial vibration and often a stronger 2 orders component. By comparing phase readings, multi-axis vibration levels, and waveform shape, a technician can confidently distinguish the 2 faults. The slide reinforces the requirement of using both frequency and time waveform analysis for proper diagnosis. A critical diagnostic challenge is that several unrelated conditions can also produce 2 orders running speed vibration peaks, leading to misdiagnosis. These include bent shafts, cocked bearings, looseness, resonance interactions, and eccentric components. This slide emphasizes cross-checking vibration signatures, analyzing phase data, and verifying directional patterns to prevent false conclusions. Proper interpretation requires engineering judgment and experience with typical machine behavior across load conditions. Temperature effects on misalignment, time waveform analysis of misalignment. Thermal growth can cause a machine that is aligned cold to be misaligned during operation. Machines heat unevenly, especially between drivers and driven units, causing one shaft to expand more than the other. This section explains how to predict thermal growth, compensate for thermal offsets, and use infrared thermography as part of the diagnostic workflow. Misalignment related to thermal effects often shows changing vibration patterns as the machine warms up, reinforcing the need for dynamic alignment considerations. Time waveform analysis provides deep insight into misalignment, revealing repetitive impacts, waveform modulation, axial-radial coupling effects, and non-sinusoidal characteristics. Misalignment often causes a distinctive pattern of repeating peaks, clipped waveform tops, or modulation envelopes. The slide explains how to interpret these patterns and how time waveform analysis complements frequency domain interpretation. Real-world applications highlight how waveform examination detects misalignment cases that would otherwise be misinterpreted using only spectrum data. This case study illustrates a real operational example involving cooling water pump number 2, highlighting the diagnostic process from initial symptom observation to final misalignment correction. The example includes vibration trends, waveform indicators, spectrum signatures, and the root cause identified through shaft measurement and thermal evaluation. The case reinforces the importance of comprehensive data collection and demonstrates how misalignment can coexist with secondary issues such as soft foot. Soft foot occurs when one or more machine feet do not sit flat on the baseplate, distorting the machine frame when bolts are tightened. It can mimic misalignment symptoms by shifting the shaft centerline and generating one order and two orders vibration. This slide explains how to detect soft foot using feeler gauges, dial indicators, or laser alignment tools, and why correcting soft foot is essential before alignment. A bent shaft produces strong one order and two orders vibration components and may resemble misalignment due to its cyclic bending. Time waveform analysis often reveals periodic asymmetry consistent with shaft deformation. This slide explains diagnostic indicators and how to differentiate bent shafts from angular misalignment by examining phase and harmonic behavior. A cocked bearing produces uneven load distribution, causing high axial and radial vibration that resembles misalignment. This slide describes how improper bearing seating leads to skewed vibration patterns, uneven temperature rise, and premature bearing failure. Differentiation requires examining load zone patterns, directional vibration behavior, and coupling condition. Misalignment diagnostic flowchart, diagram placeholder, vibration signature examples, diagram placeholder, thermal growth illustration, diagram placeholder, summary, final key points, final slide. This slide contains a placeholder for a diagnostic decision flowchart that guides technicians through identifying misalignment versus other similar faults. The flowchart typically includes decision points involving vibration direction, dominant frequencies, time waveform characteristics, and physical signs such as heat, coupling wear, or abnormal noise. While the diagram is not embedded here, the placeholder guides users to insert an engineering diagram consistent with written practices. This slide reserves space for vibration signature diagrams including one order, two orders, and harmonic patterns characteristic of misalignment. These diagrams help visually compare misalignment-related signatures with unbalance, bent shaft, and soft foot fault patterns. Users are expected to insert actual plots from their vibration analysis software or from machine data. This slide provides room for inserting a thermal growth diagram illustrating how temperature affects shaft alignment. The diagram typically shows relative movement of machine components during warm-up, highlighting the importance of hot alignment versus cold alignment settings. The summary slide consolidates the major learning points from the presentation, including identification methods, common pitfalls, related fault conditions, and the need for multi-axis vibration measurements and waveform analysis. It reinforces how misalignment affects machine performance and reliability. This slide highlights essential takeaway messages such as the importance of proper installation, regular alignment checks, thermal compensation, and distinguishing misalignment from other faults. It emphasizes the combination of frequency, phase, and waveform analysis as the most reliable diagnostic methodology. The concluding slide signals the end of the presentation and may be used for questions or discussion. It typically includes contact details or a final professional closing statement.